This lesson, we are looking at 8.2 vectors in projectiles. To be honest, this is not too far away from what you've learned in chapter 6 about projectiles. We can still use the same method, but the difference here is one is given in vectors instead of giving it in u, like a u cos theta, u sin theta. It's very different. You can see the vectors involved. And second one is about the position vector being relative to one point and the other. Now, we'll talk about that point after we recall the Suvat formula, or should we say the Ruvat? Okay, Ross. Anyway, Ruvat. So if you don't know what I'm talking about, Ross, go and watch Friends. Right. So the first one that you should recall is R equals R naught plus VT. Remember, V is a constant velocity, so you can't use this without the constant velocity, the word constant velocity. The next one is V equals U plus AT. And one is R equals UT plus a half AT squared. Okay, right. So next we talk about position relativity. Now, so think about this. On a coordinate axis, okay, we know that point is the origin O. Okay, let's say this point is 5, 8. Okay, now this point is only 5, 8. So this point A. So let's call this point. A. Okay. So on the side in here, point A is 5i plus 8j relative to O, because we only do 5i plus 8j when you start counting from O, right? So 5 to the right and 8 upwards. Now, however, okay, what about this point? Let's say we call it point B in here. Okay, this point B has a coordinate 0, 2. The question is, what is the position of position vector of A relative to B? So if we have to describe the position of A from O, it would have been 5i plus 8j. But what if we started with B? What would be the position vector B relative to B? Okay, from B. It would be 5i plus 6j, wouldn't it? 6j, because it's only going 5 right and 6 up. Okay. Now, this is what we call about the position relativity. When you describe a position, it must be relative to a point, because without a point, you can't describe things. So it's like I tell you, in a classroom, I'm standing 5 meters. You will be questioning 5 meters of what? 5 meters away from the, let's say, the chair, the teacher's desk. Then you would have a better understanding where I am, even though you don't know where exactly I am. Okay, but if I tell you I'm 5 meters away from the table and 6 meters away from the window, you probably have a better idea again. So you can see it's 5 meters away from a table, 6 meters away from the window. So you can see it's relative, it's all relative to a point. All right, now we will play around this idea today on top of projectiles, obviously. Example, a ball is struck by a racket which has position vector 20j relative 20j meters. So you can see point A, we start from 20 meters high, relative to fixed origin O. Immediately after being struck, the ball has velocity 5i plus 8j. So you can see it's a projectile. After being struck, the ball is travels freely under gravity until it strikes the ground at point B. Find the speed of the ball 1.5 seconds after being struck. So what we do in here is projectile. The method is double Suvat. Now we do have to specify this is from A to B. Okay, because you've got 2 points that you got 2 points in A and O. So just be, when we do Suvat, it's better to write down the journey you're calculating. We're calculating from A to B. So double Suvat, we'll set it up. See if you remember anything about double Suvat. Okay. What we know is, okay, on a projectile, first thing is AX is 0 and AY is negative 9.8. Right? So that's a given. U is 5i plus 8j. So we can break it down to UX is 5, UY is 8. What else are we given? we are given, okay, so 20 meters. How do we use the 20 meters? Well, from A to B, we have descended 20 meters. So SY will be -20. We want to find the speed of the ball. Speed means Vx and Vy. So speed, just a bit of recall, speed equal to the square root of Vx squared plus Vy squared. Speed is the magnitude of the velocity vector. Okay, so what we need to do is, okay, 1.5 seconds, balls, 1.5 seconds, 1.5 seconds. So let's do that. We need to find Vx and Vy. So let's do the X first. So we can use V equals U plus AT. So V is unknown, U is 5, A is 0, times T is 1.5. So V is 5 for Vx. What about Y? V equals U plus AT again. So V equals 8 plus -9.8 times 15 at 1.5. Put in a calculator. That should give you, I can't read my writing. It should be 6 point. Hang on a minute. Can't read my writing. Let me put in a calculator. Yes, it's -6.7. I'm sorry, I couldn't read my writing. -6.7. So it's negative. It makes sense because if going up, you can see it's +8, and coming back down will be a negative in terms of vertical position. Right. So therefore, the velocity, we're going to write velocity essentially equals to 5I minus 6.7J. Now, this step is not required, but I'm just, showing you the understanding, the completion of the notes, the steps in between to clear your concept. So therefore, the next thing is we want to find the speed. The speed is the magnitude. To find the magnitude, we're going to do square root of 5 squared plus -6.7 squared. You can put negative or not because squaring will cancel negative anyway. Put in a calculator, you should get 8.36 meter per second in 3SF. Okay, right. And that's the speed, right? Part B, find an expression for the position vector R of the ball relative, if you have a highlighter, highlight the word, relative to O at the time t seconds. Now, to find a position vector, essentially that's finding out the displacement, okay, in the double suivar. So what we want to do is we want to find the Sx from part A, from double suivar in A. Okay, so from part B, we're going to use the double suivar in here to help us. All right, so use a pencil in here. I want to find Sx. Find Sx. Right, so to find Sx, we're going to do in X, we're going to do S equals UT plus a half AT squared. Oh, actually, sorry, at t seconds. Sorry. I'm glad I told you use a pencil because we can't do this. Actually, let's rub it off. I'm so sorry. We have to do it again. Now, the reason we can't use this double suivar. Can anyone tell me why can't we use? Oh, think about this. Can anyone tell me? I'm not going to listen to it anyway. Can't hear it. Why can't we use double suivar? What's this double suivar in particular? The reason is because this double suivar is particularly tailored from A to B. Now, I want to find a position vector, this suivar, from a journey time t seconds. This journey only lasts for 1.5 seconds, so we can't use this because this double suivar is only for the t equals 1.5. So if we need a new time, we need a new suivar. So part B, okay? So this is from A, okay? So this double suivar is from A. X, Y, suivar. A is 0. AY is -9.8, UX is 5, UY is 8. Is the V the same? V is V5 and -6.7 we found in part A? No, because this velocity is only for point B. We're not going for point B. Okay, we're going to order point somewhere in this line, so it's not a specific point. But we know this suivar is from A. Now it's quite important from A. Want to find S. T is unknown, but we'll put a T because time t seconds. So I want to find Sx and Sy because position vector means to find displacement. So in the X, we do S equals UT plus a half AT squared. S equals 5T. For Y, S equals UT plus a half AT squared again. Some of you might question, why do you have to always write a formula? One, it helps me to remember it. So in the exam, when I realize, okay, it doesn't I've done it so many times, it doesn't kind of make sense if I put a minus in there. Okay, no, it's maybe it's a little mistake. And two, by writing this down, when I do a substitution, I can just put it in there. It's like, when it's a baby, you see some pegs, and then you see different shapes. You put the pegs into the right shape. It's like you're doing the same thing in here. When you see S, you substitute S in there. So you can just do it one by one. You don't have to do two things. You just do substitution the next step in your brain, rather than remembering the formula and do substitution, which makes it a lot quite easy for mistakes. So S equals U, which is 8, T is T, plus a half times negative 9.8 T squared. So S equals 8T minus 4.9 T squared. Now, students with a worse handwriting, which is quite rare to find, but I've seen them, is that your S and 5, just be careful, they're not the same. Some students write the S like a 5, and then 5 somehow becomes a 3, a 9 and a G. If you're those S5 gang, or like a G9 knob gang, G9 gang. So just be aware of that. So once we've done that, so we can combine the X and Y. Okay, so therefore the position vector relative to A is relative to A because the suba comes from A. R equal 5T, so the X is the I, plus the Y, 8T minus 4.9 T squared J. Or you can write as a column vector 5T, 8T minus 4.9 T squared. Okay, so meters, because that's the displacement. But the question wants a relative to O. So the position vector relative to O is, now the position vector of A is 20 meters above O. That means if we have to start counting from O, we have to add another 20 meters vertically, because this position vector we got is from A. In other words, if we go back to the when we describe about the relativity in the beginning, we're given 5i plus 6j instead. So we're given this position vector in terms of a point relative to a point above O. So 5i plus 6j. If I want to find a position vector relative to O, which is 2 or 20 above, below B, then I have to add the 2, so it becomes 8j. Same thing in here. Relative to A is this 5t, 8t minus 4.9 t squared, relative to O, which is 20 meters below. That means we have to add 20 meters because A was 20 meters above O to begin with. So relative to O will be R equal 5t and 8t minus 4.9 t squared plus 20. So what I want you to do is I want you to pause the video and write a little note to yourself in here. Where's the plus 20 come from? So where does the plus 20 come from? Where does it come from? Okay, right. So that's the answer for part B. Part C, hence determine the distance from O to B. To determine the distance from O to B, well, what we know is, look at B. B is on the x-axis. So B is on the x-axis. That means the y coordinate is going to be 0. So right in here, part C. Right, so part C. Notes for you. B is on the x-axis. So therefore, the position vector, that means the position vector, you can describe position vector like a coordinates. The coordinates of B, but we can't say coordinates in here because there's no coordinate. It's a vector plane. So position vector of B is something I plus 0j. So what we can do is we can make the j component of R equal 0. So therefore, 8t minus 4.9 t squared plus 20 equals 0. The j component of position vector is 0. So what does it become? This is a quadratic. When you put in a calculator, be mindful, this is your A value. The minus 4.9 is your A value. Student will make silly mistake to put the 8 as an A because the t squared has to put in the front first. If you put in a calculator, I would suggest you put in a calculator. Try it. You should get t equals to 2.995. I don't know what's the other answer. I didn't write down, but anyway, doesn't matter. I think the other one is negative. So 2.995. Therefore, but that's not a position vector. We need to find the I value. So the I value is, so 5 times 5t, so 5 times 2.995 equals 15 meters. So therefore, OB equals 15 meters. All right. So that's how we find it. Okay. Next example. A ball is projected from a point A at the top of a cliff with position vector 25j meters relative to the base of the cliff. I'm going to ask you, okay, pause the video now, have a read through a question, and then we'll go through part A together. Okay, right, question A. Suggest with reasons which of these two modeling assumptions is more realistic. So where are the two modeling assumptions? First of all, the first modeling assumption is the ball is modeled as a particle moving through in gravity. That's the first assumption. The second assumption is the sea is modeled as a horizontal plane. Maybe you can think about which one is more realistic. So which one would you put it down in the exam for 2 marks? The answer actually is both answers are acceptable with a valid reason. It's like choosing between conservative and Labour. We're choosing one between two lesser evil. Right, depends on the time. I'm not political. Anyway, so in here, well, why is it two evils in here we're choosing? Because these two, both assumptions does not make any sense at all. Well, one, okay, so if we say the ball model as a particle is more realistic, then, so we say assumption 1 is more realistic. That means we're saying that assumption 2 is less realistic or unrealistic. Well, you just have to justify why. Simple, because how likely is sea is going to be horizontal? You know, the sea has waves. You know, how likely is the sea going to be horizontal? So you can say that. So let me type it out. Okay, here's say that. Okay, the ball as a particle is more realistic because the sea surface is very unlikely to be flat due to waves. All right, or you can say if you think the sea is modeled as a horizontal plane, which is more realistic, then you just have to justify the first assumption is unrealistic. Well, it's unrealistic because moving freely under gravity is not quite possible. It's quite hard to achieve. You can achieve it in a very tight, well-controlled experiment center or, you know, laboratory, but how likely? You know, there's air resistance, that kind of stuff. So we can say that as well. Right, so you can say it. So in the first answer, I changed my wording a little bit. You should say the ball moving freely under gravity is more realistic because that's the assumption. It's not about the particle; it's about the freely under gravity. So, or you can say the sea is as horizontal plane is more realistic because the air resistance has to be factored in, which makes the ball moving freely under gravity unrealistic. All right, but both of them are, you know, are equally fine. So you can choose one. Right. Question B: find the velocity of the ball at point B. So 6 marks and 6 marks for part C as well. So part B, find the velocity of the ball at point B. Well, we can see the journey is from A to B, so we'll do that. So double sweep up from A to B. Okay, no nonsense. Double sweep out. Pause the video, try to fill out a table, okay, and then you can check the table with me. So from A to B, my AX is 0, AY is minus 9.8. My UX is 3P, my UY is P. My SX is, do I know SX? Do I know SX? Yes, I do. QI plus 10J meters from the question. So QI plus 10J. So that's, this B is QI plus 10J. So in terms of SX, we've moved Q. In terms of Y, we've moved. So A was 25, comes down to 10 is minus 15. What do you want to find? I want to find velocity vector. So that means, and we know T is 2 as well. So that's your complete table. I want to find V, so Vx and Vy. I want to find the vector, so I don't need to find the speed, but I still need to find the vector. Now, so from the X point of view, let me do it here. From the X point of view, we can use V equals U plus AT. So V equals U, 3P, okay? And V equals U plus AT. Actually, what do we want us to find again? Velocity of the ball. Yeah, okay. For what's that? For Y, I use V equals U plus AT again. So V is unknown, U is P, A is minus 9.8 times 2. So V equals P minus 19.6. Then you realize I need to find the value of P. So how do I find that? Well, can you see that in the Y column? I can find P because I've got more information I need. If I want to find P, all I need is to use S, A, and T to help me. So I'm going to do more steps. I need to find P. So to find P, I'm going to S equals UT plus half AT squared on Y. So on the Y-axis, S equals UT plus a half AT squared. S is negative 15. U is P. T is 2 plus a half times negative 9.8 times 2 squared. Solve the equation. You should get P equals 2.3. Okay, do it yourself and see if you got P equals 2.3. Now, since I got P equals 2.3, I can work out X quite easily. So V, so therefore the velocity, is 3P. So V equals 3 times 2.3, which is 6.9. So equals to, so V equals 6.9 I. And for the y-axis is 2.3 minus 19.6. That will be minus 17.3 J meter per second. And that's the velocity vector. Okay, so what I did was I substituted P into here. So I got minus 17.3 J. Right. Part B, a remote control bolt leaves O at the same time the ball is projected and travels in a straight line towards C corresponds to acceleration. Given the ball lands on the bolt, wow, find the acceleration of the bolt. Now think about this. Again, if you're unsure what information the question is given to you, think about the root one by one. When the bolt catches the ball, which variable does it relate to in the root? It certainly relates to the R position because they both have to appear at the same position for them to meet, right? So what we want to do is the part B. When the bolt catches the ball, it means the PV of bolt equals PV of ball. But do we know the PV of the bolt? We don't. And can we use the previous Suvat table in here? We can't, because if they both catches at C, that means I need to make a Suvat table from A to C. So let's set up a Suvat table from A to C. So from A to C, let's do that. So from A to C, X and Y again, Suvat, SUVAT, A is 0, AY is minus 9.8, we know that. And UX was 3P. 3P, we know P is 2.3. So 3P will be 6.9. And Y will be 2.3 because P. Okay, and now because we don't know how long exactly it takes from the particle or the ball travels from A to C. So time is unknown. All right, time is unknown from A to C. Now we're not interested in the distance because we're interested in this. We are interested in distance. What I'm talking about, we are interested in distance because we just said PV are the same. So we're gonna make a expression for the position vector from A to C. Okay, so let's do X. S equals UT plus a half AT squared. So S equals U 6.9T plus a half 0. So that's 6.9T. And for Y, S equals UT plus a half AT squared. So S equals 2.3T plus a half times minus 9.8, so minus 4.9 T squared. So the position vector, the PV, so therefore the PV relative to A, because we start from A, relative to A is R equals to 6.9 T I plus 2.3 T minus 4.9 T squared J. Or preferably, I prefer to make it 6.9 T and 2.3 T minus 4.9 T squared. Either one of them is fine. But that's not what we need because we need a position vector relative to O. So A was 25 meters above O. that means we add 25 meters to the position vector. So therefore, the R relative to O, so R equals 6.9t, and then 2.3t minus 4.9t squared plus 25. 20 was the previous question. 25 is this one. That's 25. Okay, plus 25 because we'll start counting from O instead of A. Right? So that's the position vector of the ball. That means using this formula, the expression 6.9t and 2.3t minus 4.9t squared plus 25, we know the position of the ball exactly second by second. If we know the position vector, the position of the ball in the first second, we can put a 1 in the t value. The problem here is, the question here is, how long we want to find out the value of t that the ball hits the ball at C. Now, C, there's a very interesting position because C is on the x-axis. So on the x-axis, it means the y equals 0. So C is at the x-axis. So therefore, the J component, the J component of R equals 0. So what it means is, it means 2.3t minus 4.9t squared plus 25 equals 0. So we can solve it. You can see this becomes a quadratic. Put in a calculator. Again, the minus 4.9 is the value of A when you solve the quadratic. You should get t equals to minus 2.04. We're going to reject that. T cannot be negative. We cannot travel back in time, even though we wish. There's so many things we should do when we're a kid. We can't. Anyway, life lesson over. We know time is 2.51 seconds. Still, that's not enough because we're not interested in time. We're interested in the distance itself. So we want to find the distance from O to C. From O to C. Isn't that, hang on. So from O to C, we know the position here is 6.9. What do I want us to find again? Find this. I'll find the acceleration of the boat. We'll find the acceleration of the boat. Sorry, find the acceleration of the boat. Anyway, so when you find we can sub in to find the x coordinate of the C value. So 6.9t, 6.9t becomes 6.9 times 2.51, which is, back to 17.3 meters. So what it means is from O to C, this is 17.3 meters. To find acceleration, Zubat. A normal Zubat from O to C. Normal Zubat because from O to C is just one dimensional, just to the right. So S is 17.3 meters. Initial velocity is 0. The acceleration, want to find out time, it takes 2.51 seconds. So you use S equals ut plus half at squared again. And then you get plugged in the calculator. So 17.3 equals 0 times t. So it's a half times a times 2.51 squared. A will give you 5.50 meter per second squared. And that's the answer. Right, so let me just do a quick recap of what you've learned, what we've done in this question. Part A, I'm going to skip that. Part B, to find the velocity of the ball at point B, we do the journey. Journey you can see from A to B. Therefore, we set up a double Zubat from A to B. Want to find V, so we'll try to set up a V equation, velocity equation on X and Y. But what we realize is we need the value of P. So it's not workable without using the other values. So in the Y column, I see there are three information I can use, three pieces of information. So I can use that to work out P. So I've got P equals 2.3. Therefore, I can work out the velocity vector, 6.9i minus 17.3j. Next, that's part B. Part C. Now, actually, that's meant to be part C. Oops, I bet that's meant to be part C. Now, when the boat catches the ball, that means the position vector of them are the same. So position vector of the boat, we're going to travel from A to C because they catch at point C, they meet at point C. So from A to C, you set up a double Zubat column. Thing is, this time, we cannot use the same table because this journey is not the same. And also, the time is unknown, so we'll make T as T. We're going to set up a Zubat, an expression for position vector, and then this is what we got, but that's relative to A. How do we know it's relative to A? We started from A. So if we need one relative to O, we have to add 25. Your question might be, why do we need a relative to O then? The reason being is the boat travels from O. So you need a journey from O. Okay, so this is a position vector relative to O. At C is the x-axis, so the j component equals 0. We find out when time equals 2.51. That's where the ball reaches the point C. To find the coordinates, we substitute t into 6.9t as well to find 17.3. And then to find acceleration, we do a simple subat to work up the rest. Okay, so you can tell vectors in projectiles essentially is double subat, but the new trick you've learned here is to find a position vector relative to different points, an expression of it. This is quite a common trick that you have to learn. You can see in part B, we did the same as well to find an expression for that. It's a quite common trick, common theme. All right, so that's vectors in projectile.